Okay, we introduced magnetic fields last time, and we're going to continue to talk about magnetic fields and magnetic forces. Specifically, we're going to look at the magnetic force on a current-carrying wire. So last time we learned that moving charges experience a force when they move through a magnetic field. So it makes sense that a current-carrying wire, which is just a collection of moving charges, will also experience a force. So we want to be able to quantify that in terms of the current in the wire. And then we want to look at a very useful configuration of a current carrying wire, which is a loop. And in a loop, we'll see that there's a torque on the loop when it carries current in a magnetic field. This forms the basis for motors, electric motors. So it's a very important application of forces from magnetic fields. So that's what we're off to today. To start with, if we think about the particles that make up current, the charge carriers, and if you sort of forget everything you know about electrons and atoms and such, and just imagine, it's the 1800s and you're trying to understand the behavior of electricity and magnetism, one of the things you'd be curious about is trying to figure out what are the charge carriers in electric current. And one of the earliest discoveries of these charge carriers was by J.J. Thomson, who used what's called a cathode ray tube. So you've seen a cathode ray tube at some point. The old televisions that had the big, tube televisions, those are cathode ray tubes. And the way they work is you have a cathode, that would be the negative end of a voltage supply, and an anode, which would be the positive end of a voltage supply. So basically these are, you could think of them as two ends of a capacitor, and they're connected to a voltage supply. So you have this positively charged plate over here, the anode, and a negatively charged plate over here called the cathode. And this whole thing is in a vacuum, so that when particles, when you put a high enough voltage between the anode and the cathode, you can actually get particles to leave the cathode and get accelerated across this voltage difference. And if you put a slit through the center of the anode, then some of those particles will pass right through and form what's called a cathode ray. So it's a ray of particles coming out of the cathode. And you do this in a vacuum so that those particles can move without colliding with anything. And then over here, if you put a glowing phosphor on a screen, you'll find that those particles actually light up that phosphor. So that's what's on the end of a television display, is various colored phosphors to light up red, green, and blue. So the idea is that if you can measure the voltage between these 2 points, you can work out how much kinetic energy the particles have once they're accelerated. Because if you know their charge and they accelerate across a voltage of V, then they have a certain amount of change in potential energy that went into kinetic energy. So you have these moving charged particles with some kinetic energy. And then you can do a couple things. You can put a couple of plates here, charged plates, to produce an electric field. In this case, that electric field is vertical. And that will deflect the charged particles. So if you have a positively charged particle, it would, in this case, deflect down. And if it were a negatively charged particle, it would deflect up, because the electric field is pointing downwards. So it'll exert a downwards force on positively charged particles. So one thing you could do right away is figure out whether the cathode rays were positively charged or negatively charged. Okay, they're going to be negatively charged. We can see that because they come from the negative terminal of this voltage supply. So they're negative charges, so they're going to tend to bend up. And so if this ray was producing a dot on your phosphorus screen here, when you turn on the electric field, you're going to see that dot move up. Now, you can also apply a magnetic field, in this case horizontally, and now our moving charges through that magnetic field will experience a magnetic force. And so we can use the right-hand rule. V cross B means V cross B is pointing up, but remember our charges were negative, so QV cross B points down. So the magnetic deflection that they feel is down. So the electric force is pushing them up, the magnetic force is pushing them down, and you can dial up the strength, let's say, of this electric field here to recenter the beam. And when you do that, you know the magnetic force balances the electric force, and the particles aren't being deflected. So if we work out, first, the kinetic energy of the charged particles, which we know has to equal the change in potential energy, Q times V, where V is the voltage that they're accelerated across. That change in potential energy must equal the change in kinetic energy, which if they start from rest means 1/2 mv squared. This is the velocity of the particles after they've crossed the anode. So we can solve for their speed, little v, by just multiplying both sides by 2 over m and taking the square root. And this is how fast they're going. So we turn up the voltage, they're going to move faster. And the speed depends on the charge to mass ratio, because the greater their charge, the faster they'll be accelerated across the gap between the cathode and the anode. And the greater the mass, the more inertia they have, and so the slower they will be going. Well, if we know that's the velocity, and we know that the electric force, QE, that would deflect them up, is balanced by the magnetic force, which is a magnitude of QVB, which would deflect them down, then we can set those things equal to each other and solve for V. Right? The Q's cancel out, and the velocity of our particles must be E over B, the electric field over the magnetic field. But we've already solved for the velocity of the particles. It was square root of twice the voltage times the charge to mass ratio. So we can set those two things equal to each other and solve for the charge to mass ratio of our particles here in terms of parameters of the experiment that we can control. So the electric field that's deflecting the particles up is determined by the voltage we place across those plates. V is the accelerating voltage, and B is the strength of the magnetic field that deflects them down. So we can control all those properties, and when we adjust them such that the beam is not deflected, we can evaluate this to get the charge to mass ratio of the particles. And so that charge to mass ratio, really interestingly, turned out to be a constant regardless of what material the cathode was made of. So these particles that are coming off of the cathode are presumably parts of the cathode, parts of the metal. So you might think that like a copper cathode would have maybe a copper atom flying off of it, and a silver cathode might have a silver atom flying off of it, and those have different masses. But it turns out, regardless of what material you use for a cathode, you get the same charge to mass ratio, which suggested this flow of particles, this cathode ray, was not made up of pieces of the cathode breaking off. It wasn't made up of the element that the cathode was made up of. It was made up of something smaller, something that makes up all the different atoms that you can make up any element out of. So this, of course, was the electron, and this was the initial discovery of the electron. So actually, it was the first discovery of any particle smaller than an atom. So prior to this, the idea that atoms were made up of electrons and positrons and neutrons was not established. So later, Millikan would do the oil drop experiment that took charged oil drops and suspended them between electrodes. And by adjusting the electric field that would push up on those charged oil drops, he could offset the weight of the oil drops, which pushed down. And by adjusting it until the oil drops floated, or basically levitated, you could determine the charge on the oil drops. And when you combine that with the charge to mass ratio that J.J. Thomson had made, you now knew the charge and the mass of these electrons. And that was really the beginning of our modern understanding of the standard model of particles. Okay, so getting back to our analysis of magnetic fields producing forces on moving charges, we want to be able to describe the force on a wire. So just imagine that this curved path here is the path that a certain wire takes, and it might have different cross sections. So at one point it might have an area, cross-sectional area A1, and maybe it tapers down as cross-sectional area A2. We're going to be completely general here. And imagine our charges are flowing through this wire at a certain speed. Over here, we'll call that speed v1. And in a time dt, the distance they travel then is v1 times dt. As the wire gets narrower, the charges have to speed up to get the same number of charges through any given cross-section. So if the cross-sectional area is narrower here, the velocity has to speed up, and the distance that the charges travel in some time dt is v2 times dt, and is shown here sort of graphically on the diagram. Okay, well, what we can say is that if there's n charges per unit volume, so this is the density of charges in our wire, and each charge has a charge q. If these are electrons, that charge would be minus e. We'll just call it q here. And they're moving at some drift speed v sub d. Then the number of charges that we have is the number density times the volume. Right? That's just the number of charges. And q is the charge on each of them. So nqv is the total charge in a given volume. So if we want to consider the volume contained in this little purple cylinder here, that's the cross-sectional area times the distance that the charge is moved in our given time dt. So the cross-sectional area is a. The distance that the charge is moved was the drift velocity times time. And what that lets us do is it lets us write the current flowing in the wire, which is dq dt. It's the time rate of change of charge. And we know the charge is nqv, where v is a volume, a times vd times delta t. And then we're going to divide by the delta t. So what we're going to be left with is nqavd. That's the current in the wire. And let's just check if this makes sense. N is the number per unit volume. And A times VD, that's an area times a velocity. So that's a meter squared times a meter per second. So that's a volume per second. So N is number per unit volume times volume per second. That's going to be the number per unit per second times Q, the charge. So that's the total charge per second. It's the current in the wire. So we've expressed the current in the wire in terms of the drift velocity of the charges. And we want to do that so we can apply our QV cross B formula for the force on moving charges. Bella? Current is coulombs per second, so it's a charge per unit time. Right? So if we measure in MKS units, it's going to be coulombs per second. And this will work out to coulombs per second as well. The Q is going to be in coulombs. If the velocity is in meters per second and the area is in meters squared and N is in charges per meter cubed, this will all work out to coulombs per second. Okay, so what we'd like to do is take the total number of charges in the wire, right? That was up here, NQ times the volume, and the volume was A times the length of the wire, times V cross B. So the total charge times V cross B should give us the total force on the wire, because the force on a moving charge is QV cross B, and here we have NAL, moving charges. Well, now this NALQ, if I look up here, let's see, NQAVD is the current. So N, Q, A, and V all form a current. So let me replace those with I, and I still have the length of the wire. So I can end up saying that the, here we go, the force on the wire is I times L cross B. If you have a straight wire and a uniform magnetic field, then we can say the current in the wire times L cross B is the force. And remember, I is in coulombs per second, L is in meters, so this is going to be coulomb meters per second. Just like when we write QV cross B, Q is in coulombs and V is in meters per second, so we get coulomb meters per second cross B. So this is a way to write the force on a uniform wire. But if our wire is changing direction and the speed is changing and all that, we can generalize this and write the charge from a little chunk of the wire, dF, is I times dl, where dl is the length of that little chunk. And so the idea would be if we have a curved wire like this, we could break it into little chunks, each of which we could approximate as moving in a straight line, and then integrate all those chunks to get the total force. All right, so current in a wire experiences a force in a magnetic field that can move it. Can you think of any applications for this? Maybe some that you've heard of? Some that you're looking at right here? So a loudspeaker or speaker uses this effect. The wires that go into your speaker actually loop around a coil, and that will carry current through it. And then the cone of the speaker itself will have a magnet in it. And when current flows through that coil, the magnetic field produced by the magnet will exert a force on that coil and push it back and forth, depending on the direction of the current. And so if you fix that coil in space, Newton's third law tells you that the coil will exert a force on the magnet, and that magnet's attached to the speaker cone, so it's going to move back and forth and shake the speaker cone and produce your sound wave. Okay, so this is an application of moving charges in a wire, a current in a wire, experiencing a force in a magnetic field. So in this case, we had a loop of wire. In fact, that's a really common geometry to work with. So let's consider a current loop. And here is sort of an ideal current loop, or the conductor actually forms a loop. Now, there's no way to get the current to flow through that with the battery as such, but what you can do is you could have this connected to a battery or something out here, and we can treat the current that flows around this as if it were flowing just around this loop here, and we can sort of ignore this stuff out there. Okay, so we're doing an idealized loop here, and let's look at the forces that are exerted on this ideal loop. Okay, so first let's look at our geometry. We've got a magnetic field that's pointing straight up in the z direction, and we've got a loop that is inclined at some angle relative to the xy plane, and we're calling that angle phi. So that's just an arbitrary angle for the moment. And then we're considering current that's flowing in this counterclockwise path around the loop. So let's break this into 4 parts. We'll look at each segment of the loop, each side of this loop. And it's a rectangle where the short side I'm calling B, and the long side we're calling A. And first, let's think about the direction of the forces. So in this top side here, where the current is flowing, I guess this is in the y direction. Here's our y-axis. If the current is flowing in the y direction, and the magnetic field is along z, let's use the right-hand rule to find the direction of the force that's exerted. So our equation is dF equals I dl cross B. And so we want to point our fingers in the direction of the current loop. It's flowing this way, and then we want to curl them to point along B, which is up. So point them along the direction of the current, orient your hands so that when you bend your fingers to point up, your thumb will show you the direction of the force, and in this case, that's along the x direction here. Right, so that's the x direction. On the bottom part of the loop, the current has turned around and is going the other direction. So that's just going to flip the direction of the force. When we point our fingers along the path that the current is going and orient our hands so that we can bend our fingers up, our thumb is going to be pointing along the minus x direction. And of course, this length here, A, is the same as that length there, because this is a rectangular loop. And the current here is the same as the current there, because it's just two parts of the same wire. They're in series. Which means, if I look at this expression, the magnetic field's uniform, the current's the same, and the length of wire that I would integrate over is the same. It means the magnitude of this force and the magnitude of that force are going to be equal, but they're pointing in opposite directions. Okay, so those are going to cancel out. Now let's look at the force on the sides. So first, this front side, where the current is going sort of up and to the right. Point your fingers along the current and orient your hands so that you can bend them to point up along B, the magnetic field, and your thumb will point along the minus y direction here, which gives us the direction of the force. And then over on the other side, the only thing that's changed is the direction of the current. So instead of starting with our fingers pointing this way, we're starting with them pointing that way. So we've flipped this around and gotten a force on the back that points along plus y. So this force and that force cancel out. And so what we found is that the total force, when we add up the four forces that we just found on this current carrying loop, are 0. Even though each part of the loop has a force on it, the magnetic field is not going to make that loop accelerate in one direction or the other. It's actually going to try to stretch out the loop. Right? So if our wire is not rigid, if this is just a flexible wire, it might get pulled out into a bigger, maybe in a circle or something like that. But there's no net force on this loop. Now let's look at the torque on the loop. If we go back and look at what these forces do, this force and this force are acting along a line, so they don't produce a torque. If you recall from Physics 50, torque is R cross F, where the magnitude of torque is the lever arm times the force. If we look at these two forces, they're not acting along a common line, right? One is acting along the bottom plane, one is acting along the top plane. They're displaced, and they're going to cause a torque. So if we think about what effect they would have on this loop, they're going to try to twist it, right, to be in the xy plane. So that's a torque. Okay, the magnitude of that torque, let's calculate the torque around some axis. Let's pick this point right here as our axis. If we do that, then this force doesn't contribute a torque. But this force up here does. And its lever arm is the distance between that force and our axis. It's this distance right here. So here is the width of our loop is b. So this distance between these 2 points is b. This angle here is phi. So this distance is b sine phi. And likewise, this distance here is also b sine phi. That's our lever arm. So the torque becomes b sine phi times the force. And the force up here that I'm plugging in, I can say is the current times the length. If I were to integrate that length from one side of this to the other, that would just give me a length A. And it's perpendicular to the magnetic field, so that cross product is just going to be have a magnitude that's equal to the magnitude of dl times the magnitude of b. So we're getting the magnitude of the force is IA times b. So let's plug that into here. And we can say the torque has a magnitude of b sine theta, that's lowercase b, times IA uppercase b. And I'll rearrange this a little bit. I times AB times B sine, I wrote theta before, but it's actually phi in the diagram. So let me change that back to phi. Okay, so this first term is the current in the loop. This next term is the area of the loop. And then everything else depends on the environment that it's in. So we can take this expression for the torque on the loop and separate it into two parts. One that depends on the loop itself, and we're going to call that mu. So mu here is what we call the magnetic dipole moment of our current carrying loop. And mu, we're going to give it a direction. We're going to say it points along the direction of the area vector. So remember when we did Gauss's law, we talked about the area vector. When you have an area of some surface, in this case, the surface bounded by the loop, we can consider the area vector to be perpendicular to that, so pointing perpendicular to the loop. And for the direction, we're going to take the direction that current is flowing around our loop, and we're going to take our right hand and curl our fingers in that direction. And that will leave our thumb pointing in the direction of the area vector. So that's another use for the right-hand rule. We're using it a little differently than we did with cross products. But whenever you have something that's curling and something associated with that that's straight, we can apply our right-hand rule that way. So we curl our fingers in the direction of current. Our thumb points outwards. So that's going to be the direction of the area vector. And that's also going to be the direction of our magnetic dipole moment for our loop, mu. Okay, so that's shown here. So the reason we do this is it simplifies a lot of the equations that we have for the torque on a loop or the potential energy of a rotated loop in a magnetic field. So what we can say is that the magnetic torque that we're feeling, that the loop feels, is IAB sine phi. We had that right here. IA times B sine phi. That can be separated into parts that depend on the magnetic field, so the B, and parts that depend on the loop, which is I times A. And we're calling that quantity mu. And if we do that, this torque can be written as mu cross B. Right? The mu gives us the IA, the B gives us the B, and the cross product gives us the sine of the angle between them. Okay, and what that tells us is if mu is aligned to the magnetic field, in this case, the magnetic field we're pointing along Z, if our loop were in the xy plane, then mu would point along the direction of the magnetic field, and the cross product would be 0. There would be no torque. And that makes sense because as we've drawn it, if we rotate this into the xy plane, then there's no longer this lever arm, this b sine phi that we had before. So that's the torque, and it's going to be a maximum when mu is perpendicular to b. So if the magnetic field is pointing up and our loop is oriented as shown here, that's when there will be the maximum magnetic torque, because on the top we'll have a force pointing sideways, and on the bottom we'll have a force pointing sideways, and that'll produce the maximum amount of rotation of our loop. Bella? If the loop is perpendicular to the direction of the magnetic field, so the magnetic field points up, and the direction of the loop we'll consider, using the right-hand rule, to be sideways. If those things are perpendicular, we get the maximum torque. So if we had this loop of current-carrying wire and we put a magnetic field on it, what do you think the loop is going to do? Is it going to move? If so, how so? First of all, is it going to fly away? No, because there's no net force on the loop. Is it going to rotate? Yes, because there is a torque. And it's going to rotate to try to align its mu vector to the magnetic field. Right? So it's going to try to align to that magnetic field. So if the magnetic field were pointing up and mu is pointing this way, the torque would be to the left. And a torque to the left means it's going to rotate like so to try to align mu to the magnetic field. So we can understand conceptually what a current carrying loop will do. It tries to orient itself such that its magnetic dipole vector points along the magnetic field. So I want to do a quick visualization of this, an example, a demonstration, I guess, call it. Here we go. So I've got this current carrying loop right here. There's actually many turns of wire wound around this bar, and so there's several loops of wire. And let's see, let me highlight it this way. Okay, so there's the loops of wire. The wire comes up and touches try to get a better view of that. It touches these metal electrodes along the cylinder at the top. You can see there's a gap right there between the left and the right electrodes. And those electrodes make contact with these metal tabs. So current's going to flow in through these wires, through the metal tabs, onto the barrel electrodes, down through the wire, and then back up the other direction. And so if I send current through that, and there's a magnetic field provided by this large magnet over here, there will be a torque that tries to align the loop to the magnetic field. So this is free to rotate. So it's going to rotate. And when it rotates through 180 degrees, it changes which of these two electrodes comes in contact with the positive terminal. So it reverses the direction of current. And now it gets a torque in the opposite direction, and it will try to rotate another 180 degrees to align to the magnetic field. And then that whole system repeats, and we've got an electric motor. Okay, so let's turn on the current. And we have a stalled electric motor. It's aligned to the magnetic field, so I need to give it a little bump. There we go. Now, as I move the magnet away, it stops spinning because there's no longer a force on it. As I bring the magnet closer, it starts to spin again. I can also change the speed by turning up the current or turning the current down. And I stalled it, so I give a little tap to get it going again. But that's the this effect of the torque on a current carrying loop in a magnetic field in action. Okay, so what I'd like you to do at this point is to try to work in a group to prove, or at least to verify, what we just learned, that the torque exerted on a current carrying loop is mu cross B. Okay, so here's a diagram showing a magnetic field going from north to south with a current carrying wire in it. The direction of the current is, it's kind of hard to see, but there's arrows pointing along this path here so that it's going clockwise. And the angle of the plane of the loop with respect to the magnetic field is theta. And I would like you to do basically what I just did, which is to first calculate the force on each of the four sides of this wire. So we'll use a width of W and a length of L for the size of our wire. And once you have the force on each side, compute the torque using R cross F. And then compare your results to what you get when you use torque equals mu cross B, where mu is IA. And see if you get the same results. And if you work in a group, you can sort of split up the work so that you each attack it from a different direction and see if you get the same results. Okay, so I've put my work up on the board so you can compare. It's tricky because we have to really think in three-dimensional space. It can be difficult to draw these things. But when we looked at the loop, I worked out the force on each of the four parts. So there was this bottom part where the current was flowing right to left. And I said the force, I'm going to use this IL cross B equation. So I have I times the length of the wire is W, the width of my, here it is, the width of my loop. And B is the magnetic field, but the cross product tells me I need the sine of the angle between L and B. So here's L, here's B. The sine of the angle between them, here's the angle between them. The sine of this angle is the same as the sine of theta. Or I'm sorry, the sine of this angle is the L cross B. Yeah, that's this angle here. If I call that phi, then I have the sine of 180 minus phi, which is theta. Okay, so that's the force on this segment. The force on this segment is going to be the same magnitude because it's parallel. But the direction, when I do the right-hand rule on I cross B down here, I have I cross B is going to give me a force that's pointing up. And on the top segment, I'm going to get a force pointing down. So on the top segment, our current is pointing to the right. So you point your fingers along that wire. You orient your hands so you can bend your fingers to point towards the south pole of the magnet, so along the magnetic field. Your thumb should point down. Okay, so I've got the direction indicated by these arrows. And then when I calculate the force on the sides, so on the left side here, my current is going up. So I'm going to use IL cross B, where I start with my fingers pointing up. I curl them to the right along X, and my thumb points along the minus Z direction. So plus Z was out of the page, so minus Z was back. So the force is going to be back on the left, and on the right, because I flipped the direction of the current, I'm going to flip the direction of the force, and it's going to be outwards. And now the magnitude I'm going to get from IL cross B, but L is pointing along y, and B is pointing along x, so they're perpendicular. So the sine of the angle between them is 1, and I just get the magnitude of the force is IL times B for that cross product. So I have IL times B pointing back on the left, and ILB pointing forward on the right. And I've labeled those force 1, force 2, force 3, and force 4. And now I can calculate the torque that each exerts. So we have to pick a point to calculate the torques around, and this time I chose the center of the loop. There are other points you could choose. But if I do that, force 1 and force 3 don't exert any torque because they act through the center of the loop. So they produce no torque. Force 2 over here on the left side of the wire, because it's acting at a distance from my axis, it's going to produce a torque. So there's this force, ILB, so force 2, times the lever arm, which is this distance here, which is just half of W. Half of W is this distance, times the cosine of this angle theta. So I get half of W times the cosine of the angle as my lever arm, the distance from the line of the force to my axis. And I'll use the right-hand rule to figure out the direction. This force is trying to produce a rotation. If I do R cross F, that's pointing down. Or I can say it's trying to rotate the thing as shown by the magenta arrow on top that circulates around sort of clockwise when seen from above. And that is a downwards torque. So I'm going to denote that that's in the minus y hat direction. And then I can do a similar thing over here for force 4. The force is in the opposite direction, but because it's on the other side, the right-hand rule gives me the opposite direction, and those two opposites cancel out, and I end up with a torque in the same direction. And if I add up these two torques to get the total torque, where the forces have magnitudes ILB, I'm going to get ILB times W over 2 times 2, because there's two forces producing torques, so I just get W, cosine theta in the minus y hat direction. Bella? Cosine theta comes from the right hand, well, from the fact that the lever arm for this force is the perpendicular distance from this line of the force to my axis. So it's this distance right there. W over 2 is the distance to the wire, but only a fraction of that represents that perpendicular distance. And it's, if this angle is theta, it's W over 2 times cosine of theta. If I draw it from above, it might be clearer. So this distance was W over 2, right there. My force was acting like this, and the lever arm was this, where this angle is theta. So the lever arm was W over 2 cosine theta. Okay, so I have this expression. If I try to compare it to mu cross B, which was the other way to calculate this, mu is just a vector that is going to point in a direction determined by the right-hand rule. I curl my fingers around the direction of the current loop, and my thumb points sort of back into the left. So that's the direction of mu, like that. And I've drawn this as a top view. Here's my current loop, and here's mu, pointing back into the left. The magnitude of that is I times the area. The area is W times L. And when I cross it into B, I get the magnitude of mu times the magnitude of B times the sine of the angle between them. And the angle between mu and B is my theta plus 90 more degrees. So I have to consider the angle that I'm using here. And sine of 90 plus theta is the same thing as cosine of theta. So I end up with an expression here that matches my expression there. Any questions? Okay, then we will stop here and we will do our chapter 10 part 2 quiz.